Lesson 15 focuses on the local buckling of steel columns. A column must also be designed to prevent local buckling. When thin metal plates are used to carry compressive load, they are susceptible to buckling about their own weak axis due to the relatively small moments of inertia about those directions. Shown as a small length of a W shape, a W4 by 13 actually, the smallest W shape available. It was subjected to a uniform compressive stress. Due to its short length, global buckling was not possible. At high levels of compressive stress, both the web and flanges buckled locally. Note that the buckled elements prevent the cross-section from carrying any further load. Design provisions for local buckling of columns, as well as other members that are subjected to compressive stresses, such as beams, are given in AISC Chapter B, Section B4. AISC uses two classifications for column local buckling. Non-slender, which means that the stress element at the time of local buckling is in the inelastic region of buckling. This will happen at relatively high stress levels, so high that the column will buckle globally before it can buckle locally. Slender. This means that local buckling will occur when the stresses are in the elastic region, below the levels where the residual stresses influence column behavior. When a column is classified as slender, local buckling will usually control and the design compressive strength is reduced. Two types of cross-sectional elements are defined: unstiffened and stiffened. Unstiffened elements are supported along only one edge parallel to the direction of the compressive force. For a W shape, these are the half flanges. For a WT, the stem or web is also included as an unstiffened element. Stiffened elements are supported along both parallel edges in the direction of the compressive force. The webs of the W shapes are classified as stiffened elements as well as walls of HSS shapes. The slenderness ratio for local buckling is the width to thickness ratio. This is similar to L over R for global buckling. These slenderness ratios are compared to the slenderness limits as specified in section B4 and table B4.1a. As long as the slenderness is not exceeded, local buckling will not occur and the column can be designed for global buckling. Shown are the local buckling provisions for W shapes. Note that the slenderness ratio for the flange or unstiffened element is half the flange width divided by the flange thickness, which must be no greater than 95 over the square root of the yield stress. For the web, the length of the element is divided by the dimension h, which is the height of the web minus the fillets or curved corners. This is the length of the web, which has the constant width given as T sub W. The term H is not given in the shape tables. However, the shape tables do give both slenderness ratios directly. Few W shapes have local buckling issues. Those that do are designated with a superscript C after their designation in the shape tables. The width to thickness ratios and corresponding slenderness limits for all steel members subjected to axial compression are summarized in table B4.1a on page 16.1-16 of the steel manual. It is important to note that AISC uses B over T as the general slenderness ratio for local buckling. Local buckling can also occur in members subjected to flexure, such as beams. Table B4.1b provides slenderness ratios and corresponding slenderness limits for these members. Note that these limits are different than the limits for members subject to axial compression, as the stress distribution across the cross sections are different. Since HSS shapes are also used for columns, particularly square HSS shapes, local buckling of these shapes will be discussed here. Both square and rectangular HSS cross sections are relatively more resistant to local buckling, as there are no unstiffened elements. Note that for rectangular shapes, the width to thickness ratio is given as B over T for the short side, which is actually the X direction, and H over T for the long side, which is the Y direction. The slenderness limit is given as 1.40 times the square root of E over F sub Y. For the preferred steel type of A500 grade B, this works out to be 35.2. The yield strength F sub Y is 46 KSI from table 2-4. Similar to other types of rolled shapes, those HSS sections that have slenderness ratios that exceed the slenderness limit are designated by the superscript C after their designation. Shown is a portion of the shape table for both rectangular and square HSS sections. Note that both B over T and H over T ratios are given, even for the square sections, even though they are equal. Not given in the tables are the values of B and H. If needed, B and H can be back calculated by multiplying the ratios by the wall thickness T, which is given. This ends lesson 15.